After understanding about dimensional formulae, equations, and dimensions on both sides must be equal, some numbers must be dimensionless. So after learning those things, let us do some of the real things. So now we can test the dimensional consistency or homogeneity of an equation. So x is equal to x naught plus v0t plus half a t square. So this is a equation. So where x is the distance traveled by particle or a body, t is the time which starts from position x naught. So some particle is there and this is starting from some position x naught. It has some velocity. Velocity is v naught at time t is equal to 0 and it has certain acceleration a. So this acceleration is uniform acceleration a along the direction of motion. So this is the equation given to us. Now we have to check whether this equation is dimensionally correct or not. So let us check this. So what is the dimension of x? X is distance is always length. So this has dimension of L. So right hand side after solving must have the dimension of length. Again x0 is again length. Some is some point on this path, but again this has dimension of length. Now what is this v0t? Velocity into time. So dimension of velocity is length into t to the power minus 1. This time is t. So this minus 1 and plus 1 cancels out. This also has length, dimensions of length. So this second one also has dimension of length. So length plus length. Let us check this third one, half. Because since it is a number, it does not have any dimension. So what is the dimension of a? Lt minus 2. T square, time square has a dimension t square. Again this cancels out, we get a dimensions of L. So after all the calculations of this difficult equation, what we can see, this has dimension of L, this has L, this is L and this is also L. And you know that left hand side is dimensionally L. When we add dimensions, we add this L plus L plus L. We can add quantities but dimension will remain L. Hence this equation is dimensionally correct. There may be some other problem might be there, like this factor may be correct, 1 upon 2 pi could be written there, or instead of 1 by 2 it could be written 1 by 3. So you cannot fully tell that this is correct, but at least this equation is dimensionally correct. Dimensionally there is no problem. So as the each term on the right hand side of this equation has the same dimension, namely that of length. So we have dimension of length for all of them, this and this. So which is the same dimension as left hand, hence this equation is dimensionally correct equation. So we have checked this equation is dimensionally correct. There might be other problems, but it is at least dimensionally correct. It may be noted that a test of consistency of dimension tells us no more and no less than test of consistency of units, but has the advantage that we need not commit ourselves to a particular choice of unit. So what is the benefit? Even without knowing the particular units, there might be some different units given for left hand side and right hand side, but still we can check whether this is dimensionally correct or not, and we need not worry about the conversion among multiples and submultiple of units. So with the help of this dimensional analysis, suppose x on the left side is given in centimeter, this velocity is given in meter per second, acceleration is somehow given in kilometer per hour. So these all have different units and we have to do a very complex calculation just to tell whether this number or this equation is correct or not. But with the help of dimensional analysis, because this is length upon time, this is also length upon time, so we can do this calculation, sorry, this is h to the power square. So we can do the analysis very easily and tell this equation was correct. It may be borne in mind, that means we have to consider that if an equation fails this consistency test, it is proved wrong. Definitely if this test was wrong, we get left hand side to be L. If right hand side, let us consider it, if it was LT, then definitely it is wrong. Definitely it is wrong. If this consistency fails, definitely equation is wrong. But if it passes, it is not proved right. As we have learned, the factor may be wrong, or there is some other error. Thus, a dimensionally correct equation need not to be actually an exact correct equation, but a dimensionally wrong equation or inconsistent equation must be wrong. So this is very important. So what they have said here, suppose we get a dimensionally correct equation. So it is not necessary that equation is correct. So we have two possibilities: equation might be correct, equation might not be correct. But if we get dimensionally wrong, then equation is definitely wrong. So this we can tell with the dimensional analysis. Let us understand this with some simple examples. Let us consider an equation: half mv square is equal to mgh. So this is kinetic energy, this is kinetic energy, and this is potential energy. So both are energy, both have units of joule, but let us check dimensionally whether they are consistent or not. So here m is the mass of the body, v is velocity, g is the acceleration due to gravity, h is the height. Now we have to check whether this equation is dimensionally correct or not. That means both sides are equal or not. Let us see first side. So half does not have any dimension. Dimension of m is m. V, what is V? V is L upon T. L upon T. So LT minus 1 and square of that. LT minus 1 square. So what we get? M L square T minus 2. So this total quantity becomes m L square T minus 2. Now let us check the right hand side. Right hand side would be this mass again m, g is LT minus 2, h height is again length, so this is L. So when we multiply this is m, this L square T minus 2, we get ml square T minus 2. So this equation is dimensionally correct. This equation is dimensionally correct. But again there might be some other problem. Someone might drop this term. So this equation itself is not correct. Though it is dimensionally correct, this equation is not correct. So when we get dimensional correctness, we have two possibilities: correct and wrong. But if it is dimensionally wrong, we have only one possibility: this equation is definitely wrong. Now let us solve few more examples. SI unit of energy is joule. SI unit of energy is joule, kilogram meter square second to the power minus 2. We can see from here the energy is always in joule. So the mass is in kilogram, length is in meter square, time is in second and second to the power minus 2. So in this way we can construct SI unit with the help of this dimensional analysis. That of speed is meter per second. We know what is the unit of speed. Acceleration is meter per second square. Which of the formulae for kinetic energy given below can you rule out on the basis of dimensional arguments? M stands for mass of the body. So we have given several formulae for measuring the kinetic energy, and definitely some of them are wrong based on dimensional analysis and some may be correct. Maybe some factor is incorrect, but dimensionally they are correct. At least we can rule out some of them. So let us try with each of these formulae. What are the formulae? K is equal to m square v cube, half mv square, this we know, definitely correct. K is equal to ma. K is equal to 3 by 16 mv square. So since only factor changes here, so though this formula is not correct, but we cannot dimensionally rule it out. K is equal to half mv square plus ma. So let us see what we can dimensionally say or not say. Every correct formula or equation must have the same dimensions on both the sides of equation. Also only quantities with the same physical dimensions can be added or subtracted, that we have learned. Only quantities with same physical dimensions. Mass can be added to mass, length can be added to length, and for consistency left hand side must be equal to right hand side. So we must see this consistency, the dimensions of a quantity on the right side, so that we learn that how to solve this. But there are two basic rules. Only similar quantities can be added. Mass can be added in mass, m can be added in mass, L cannot be added into mass. Also both sides, suppose this is ml square t minus 2, so then this right side must also be ml square t minus 2, then this formula or this equation is dimensionally correct.